isotopes of uranium, U slash 235 and U slash 238 are sent into a mass spectrometer with a speed of 4.57 times 10 to the power of 5 meters per second, given the mass of each isotope Mu-235 equals 3.89 times 10 to the power of negative 25 kilograms, and M equals 3.99 times 10 to the power of negative 25. The strength of the magnetic field B equals 0.848 Tesla, and the charge of each isotope Q equals 3.33 times 10 to the power of negative 19 coulombs. Coulombs of the distance V between the two isotopes after they completed half of a circular path. See page 800 through 803.
Okay, so points. It's 20 because you had a lot to say there.
Who wants those points? Dion.
Make sure he knows where to put the points at. All right, so this is a review. If you noticed, the assignment said part 2 review of what we did yesterday, right? So you might have notes on this. You might be able to finish it faster if you know what you're doing, right? Now, let's see here. We're going to go through what we did yesterday. If y'all have from yesterday, you can take some of the notes and just put it back and just change the numbers, right? As if you typed it up already. I know Mariah did. That's all she had. Almost a we-do done. So what equation am I using? Well, R, right, equals M times V divided by Q times B, which is our radius equation, right? It's how it goes in a circle for an electron. That's what we talked about there. So R is equal to the mass multiplied by the velocity, right? This is our absolute value charge times the B field, which we're going to be given in the problem, I think, right? Make sure this is working. All right, so what do? Let's talk about what each of these are so we know how to identify it in our problem, right? So R is in terms of meters, not centimeters or anything else. You have your charge, that's that word Nicole doesn't like, coulombs. So a Frenchy type word. You have your B field, that's in terms of a Tesla. And velocity is meters per second. And your mass, of course, is going to be measured always, if not in most cases, in terms of a kilogram. Okay? So there we have it. We box this off. This is really what we typed up yesterday. Should have typed up. Some of you all putting it in there. Some of you have not. I do suggest you stop cutting corners with me because I read everything. I mean, I have a lot of friends, so I sit there and grade a lot of papers. So please do it correctly. I am watching and looking. Part 1 of your notes. Known and unknown values, right? This is part 2 of your notes. What are the ingredients towards solving this problem? Well, let's pick up the pieces from yesterday, right? And maybe I should print. So if we go here to the problem, and I'm on the problem now, I'll put it on the screen for you so you can see it with me, because some of y'all will be like, where do you get that number from, right? Here's the problem, right? I'm on the we do section. So we got two isotopes, uranium 235, uranium 238. These are elements or isotopes that are important when you're trying to create a bomb or something that's explosive, right? So we kind of get into nuclear physics at this point. The first thing they give us is, of course, the velocity. And the whole problem, if you want to follow along with me, is on page 802, by the way. So let's start with the masses, right? This is, I know they said mu, but it's actually mass of uranium-235. It's an element, isotope style. And that mass was 3.89 times 10 to the negative 25th kilograms. So let's write it out. That's 3. You don't know what I'm writing, you can look at the problem to understand what I'm writing. That's negative 25, and I'll put kilogram here. We have another isotope, right? So that would be the mass of uranium-238. And that would be actually, where is it at? 3.99 times 10 to the negative 25th. So just a fraction or level up. And these are measured in kilograms as well, right? Keeping it going, so we can knock this out because we don't have a lot of time together, right? Okay, it looks like you might have homework. We have a speed, and speed is measured in terms of v, velocity. So we say v is equal to, what do we got there? We have 4.57. It's pretty fast in the spectrometer there. And that's times 10, and it's raised to the 5th power. It's pretty fast there, right? Meters per second. Continuing on, what else did they give us? Well, if you pay attention, they gave us charges, right? Or one charge for everything that's going on. And in this case, we would say Q for charge is equal to, what did they give us there? 3.33 times 10. This is the absolute value of Q, by the way, y'all. All right? Make sure that's noted. 3.33. And it's times 10 to the negative 19th coulombs.
Yeah.
All right, moving on. Well, we got to have a B field in here somewhere, right? So let's go ahead and put that in there. It says your B field has a strength of 0.848 Tesla. So let's write that out. 848. Okay, pretty good. So now the only thing we got to think about is what are we solving for? Remember, this had 3 parts to it, part A, B, and C. So I'm going to try to burn through the problem, right? And at this time, we're doing good. So what do we do, right? We got to talk about what we're looking for. So we got to find the R for uranium-235, the R for uranium-238, and the total distance. I showed you that yesterday. So let's write it out. Part A, you're going to locate the R for uranium-235, right? Something, a radius in meters. Then part B, you're going to locate the radius for uranium-238. Uh-oh. Y'all okay back there? You okay? You want to get some water? Okay. Part C. We're going to locate the total distance is the variable lowercase d is some number in meters as well. And I'm going to show you that calculation at the very end. All right, let's box this off. This is all of your part 2 notes, right? All the ingredients necessary to solve the problem. All right, let's go to part 3. We're going to have part 3, I think of part 4. Part 5 way over here probably. So it's going to be a long recording. All right, so what do we do, right? Well, we're going to use this equation, but for each isotope, okay? So we have part 3. And part A of this problem, like we said, just stating our case, what are our marching orders? You're going to solve. Please write what I write. Like, you got to explain what you're doing in these steps. Some people are not doing that. You see a series of equations going down. It's very sloppy work. Please put each segment like I did, right? Because I want to make sure you explain to somebody else, even your family members. So solve for, and like I said, R for our uranium-235 isotope. How do we do that? Well, let's look at this. We're going to use this equation, but designate it for the correct isotope. So in this case, R, uranium-235, right, is going to be equal to, use the correct mass, that's 235, right? So we're going to say we have M mass of uranium-235 here, multiplied by, the velocity stays the same in the spectrometer. So does the charge and the B field. So we're going to say our charge, which is universal for both isotopes, and the B field. plug in the numbers. So we got, let's plug it in. It's a long one, so let's write it out. Top part numerator. So it's going to be this, right? And then velocity. That's to the fifth, right? Come to the bottom. Right? What's our charge? And then, of course, our B field. Okay? So now all you gotta do is calculate. We gotta do the same thing for uranium-238, okay? So let's calculate it real quick. I'm gonna grab a calculator. Aaron, can you look in the back? There should be some calculators still in charge back there, or if not, the engineering calculator, a newer one. Were there some back there? Yeah. Okay. How's the charge look? You gotta turn it on to see. Mommy, let me see that. You gotta lock that bathroom. Okay, so let's type the top, use fraction button, 3.89 times 10x, that's going to be raised to the negative 25th power, times 4.57 times 10 to the power of 5. Coming downstairs in the fraction denominator, 3.33 times 10 raised to the negative 19th, and it's going to be multiplied all by our B field, which is 0.848. Gives a yield of 0.6. And don't forget, that's radius, so it's meters. So 0.6, very small radius, right? Very, very, very small radius. All right, this will be the end of that. Let's go to part B of the problem. How am I doing on time? I'm doing pretty good. So y'all have time to do some you-do problems and exit slip. So what do we do? Part 4 of your notes, or part B, you're simply using the same thing, right? You're just solving for a different isotope. So we need to solve, we're gonna say part B, right? You're gonna solve for your radius of uranium-238, right? Whatever that is. Using your tool. So let's designate the same and then solve, right? The velocity, charge, and the Tesla, the B field, does not change, but that mass does, because it's a different isotope. So we're going to say, hey, what is this going to be, Mr. Tyler, right? It's going to be R for uranium-238, we got to designate it correctly, is equivalent to, we have the mass of uranium-238 multiplied by the velocity in the spectrometer, all divided by the amount of charge, total magnitude, right? Absolute value, I should say, and the B field inside of the spectrometer. That's all we're doing, right? We're looking at that. This is now time to plug in the numbers. So let's do that, and we can do part C, and we're done with this puppy, right? So what is that going to be? It's going to be the radius of uranium-238 as it moves in a circular motion inside the spectrometer is going to be equal to, let's draw this out, we have, this is pretty much a lot of top, just like upstairs here. So we're changing this by 2 digits. So it's going to be parentheses 3.99, because it's 238, right? Times 10, that's raised to the negative 25th kilogram. Make sure you put all your dimensions in there, or it's not a real number. Then the velocity stays the same. Times, we have 10 to the power of 5 here. And this is a velocity, so it's meters per second. All at the top, so what's in the bottom, we have our charge. And then also the B field. Okay. Let's calculate it, and then we can get the part C. Y'all can see it's 238. Grab our calculator. This should be a quick one because I'm changing only 2 digits. I had a calculator over here. I didn't even realize it. So we're going to change it to 3.99 and the rest stays the same. And again, the sad part is this is a 0.6 again because it's not much of a change. So maybe I should do it like this. I should tell the whole decimal value. So it's going to be 0.646 here. And this is something else. I'm going to change it on y'all in a second. There's more to the decimal. Well, it's got to be different. 646. And it's meters. And if I zoom into the previous answer, it's not exactly 0.6. It's more to it. Let me go up. This is 47 over here. Clears. So this one was, make sure I'm doing it right. Yeah. So the first value is 629, not 46. 629. There we go, 629. This one though is 646. What's wrong? Oh, sure. Make sure I'm getting these decimals right for y'all. So the first value is, let me do this again, because I think that's wrong. So the first one is, let's do it correctly, 629, not this. It goes over here. 629 meters. And that's 646. Yes, I did it. Okay, 646. There we go. Because the calculator just gave me 0.6 for everything. I'm like, that's not right. So I had to zoom in. All right, last part, part C, right? This is a 50-point recording, by the way. Whoever gets it, Nicole, just watch. Last part. This is part, 5, like I said. And you're going to say part C, you're going to solve for the total distance, which is a new calculation. It is going to be factored to. So remember, this is lowercase d, right, is equal to, I think it was 2 times the radius of uranium-238, going off memory, minus the delta equation, 2 times the radius of uranium-235, off the top of my head. All right, let me do a quick reference. So we get, you have to factor it out now. You got to show all the steps. Pull up the 2. It's going to be multiplied by parentheses, radius of uranium-238 minus the radius of uranium-235. Close parentheses. Now you plug in the numbers. So what does that look like? We'll take the first one, right? This is this. 0.649 minus, and this is meters. This one, right? That's 0.629. Not much of a difference, right? But I'm going to put 0.6, 0.6. It'll be minus, it'll be 0, it'll be done. You okay, McNeese? He was like, he was waking up. Saw the eyes fluttering. Okay, so, is he trying to stay awake? Sorry to treat y'all like college students, but this is engineering, so. Oh, babies. Harrison tell you how taking an engineering course. So it's 2 times, make parentheses, and what was our first value? 0.649 minus 0.629, huh? Close. What you do? Let me see your calculator. You so close. That's not right though. You did. I knew you didn't do that. Now look at what I did. Look at the equation. That's what you didn't do. You were so close. Take 10.
I forgot the 2.
Yeah, you totally jacked that up. But you can take 10 points. You tried. You tried. You skipped one part. All right, so the total answer, Samir was so close, but it is 4 times 10 to the negative 2. It's a very small answer meters, right? And that makes sense because it's very small electrons you're talking about. So it'll be 4 times 10. Because you see an E in the calculator, that means to a power of 10. You see an E there. It's engineering notation. So it's times 10. And it's in meters. Make sure you put your dimensions for every number. Some of y'all are getting really lazy on me and not putting in what is a meter, what is a coulomb. Look, to a physicist or engineer, you'd be like, hey, 20 plus 10 is 30. And I'd be like, 30 what? Apples or bananas? What are we talking about? Right? So put your dimensions. Don't get lazy on it. Right? I am. And 50 that goes to who? Wow. Okay, who gets it though? I saw 2 hands.